Hello.
Um, okay, let's start. I hope, can you hear me? If you could drop a text in the chat confirming if you can hear me, that would be good. Okay, thank you. Uh, okay, so I see there are 12 participants. We make a note of that. Um, so this is the second week of NPTS sessions. One second. Just Let's fix this. Yeah. Okay. This is perfect. Uh, so this is the second week of NPTEL sessions, and as discussed earlier, um, this will be a weekly session, and what we'll try to do is solve problems and address doubts that you are facing in the lectures. And there are three parallel sessions being held by three TAs. Mine will be on Sunday, 6 And for the previous week's session, the video recording of the session has already been posted to YouTube on my posted on my YouTube channel, and I believe the NPTEL authorities have sent the required content to you, and the notes which I was writing down during that session, I also prepared a PDF of it and shared it on Google Drive. So the drive link, all three TAs, all of us are using the same drive link where we have separate subfolders for our content. So all of that is also you can you have access to it. Okay, not audible. I hear. I'll try to speak louder. Let's see. Hello. Okay. Yeah. I think it's okay. I'll try to speak a little louder, or otherwise maybe try to increase the output volume at your end. Voice breaking. Okay. Cell geometry. That is one question that I'm facing. Voice breaking. Okay, let me try and do something of my own. Okay. I hope the voice is clear now. It seems most people are fine. One person is facing an issue. And link for YouTube channel, I can send the link in chat over here. But you should receive it. Ideally, you should receive it from TMRF, from NPTEL itself. That's what we have been told. That like NPTEL is coordinates all of the things. So in the same way that you receive the link to this meeting, you should also be receiving the link to like, you should also be receiving the link to my YouTube recordings. So anyway, let me I'll share the playlist over here on Zoom. I'll send a playlist on in the Zoom chat, so you can view it from here. And this session, as you can see, is also being recorded and all the sessions. This is my second session, and there are 10 more sessions to go, one for each week of the course's content. And so somebody has asked me about cell geometry in short. Okay. So if you can be a little specific, maybe what about cell geometry you want to understand? So otherwise I can talk a little bit in general that 1 second. So in cell geometry, the key idea is that the cellular region is divided into hexagonal cells, right? Something which is based on the notion of Voronoi tessellation, but maybe let's go into that. But the basic idea in cell geometry is that your geographical area like you are a network operator, so you will be deploying base stations, right? So something that looks like this. I'm not the best artist here. Sorry for that, but bear with me. So the usually when we talk about cell geometry, we consider hexagonal geometry. So hexagon has, 6 sides, six. It gets a little tricky sometimes to visualize. But yeah, you get an idea, right? Every like in a different context, if you have practiced organic chemistry and if you have drawn benzene or benzene type uh, compounds, molecules, for example, you kind of have an idea how the hexagons fit into one another and things like that. So the key idea here is hexagonal geometry. And the reason hexagonal geometry was chosen is because hexagons have this nice property of fitting into one another. So we can see that if we plan this properly, then there are no coverage holes or gaps between the cells. So any user will at least find one cell to associate with, no matter wherever the user is. There is no gap and there is no overlap. These are the two important things. Right? So it's so this user is attached to this base station, this user. So let's call it. These are called base stations, right? Or BS. These are called user equipment or UE. Let's say a cell phone, mobile phone. So this is attached to this base station. So it's very clear. There is every user is attached to a specific base station, depending on which cell it is. That is how normally cellular. That is why it is called cellular communications. Yeah? Even if you remember in the older Nokia phones, at least what I remember from my childhood, is that they would show you, even in current phones, I think there are ways, but in the Nokia phones, they would show it right there, that which exact cell you are a part of. So let's say this cell would be called IIT Kanpur cell, and then if you move, then you would be able to notice that sometimes you're moving in from, let's say if this user is moving from here to here, then you will be changing cells, and so that would actually show up on the phone, that that it would show up on the phone that it would move to a different cell. And so that is because of this clear indication here that there are clear boundaries between cells. And so you will always be served by one cell, and there will never be any overlap. So let's say instead of a hexagon, if you would choose a circle, then if you would stack circles instead, then you would have circles like this. And circle is very natural, right? Sometimes you solve problems of coverage range, how long a signal can travel. So if you fix coverage range, then you will end up with circles at a fixed distance from base station and all that. So if you draw circles, you can see that between circles there will be gaps, or there can also be overlap. So let's say this base station has a larger coverage range. So there can be an overlap, and then there is confusion. Then there is some confusion that if there is a user over here, which cell does it belong to? So you want to, at least in the traditional cellular communications paradigm, you would want to avoid these confusions. You would want to avoid these confusions, and you would want to have single cell attachment and single, and so the hexagon shape was chosen. That's why hexagon is the chosen shape. So you will not have any overlaps. It will all be very clear. So does that answer your question, Abhishek? You believe? That this is in general. Now, specific, how will you do the mathematics and all? I need to understand where you are facing up, what concept. If you could be more specific, no problem. Okay, I got a query that question 15, what is meant by worst case scenario, your assignment situation. Okay. So worst case scenario is, so just try to give an idea. I won't exactly solve it for you, but the key idea, so this refers to question 15 of the assignment. And just to be clear, I'll re-emphasize this again. I told it in the last session as well. I am not supposed to give you solutions to the assignments. Assignments have to be solved by you, and the mathematics has to be worked out by you. What I can do is help you understand concepts or help you solve some doubts, help you sort out some doubts, and maybe give you some hints. That's all I can do. Beyond that, solution, the working out has to be done by you. So I might sometimes solve similar problems to assignments, but I won't be solving the exact same problem. Just to be clear. So worst case SIR scenario means that, so let's just conceptually understand this. What is SIR? You have signal power, right? Signal, you have signal power, and in denominator you have interference power, right? I hope this makes sense, right? So signal to interference, SIR stands for signal to interference ratio, right? And so that is signal power divided by interference power. Now, so what is signal power for any user? Signal power is, let's say we have user in cell C0, right? So I'll just write it down. User in cell C0, and there are other cells. Usually in hexagonal system, you have 6 co-channel cells, right? In 6 directions. 1, 2, 3, 4, 5, 6. So it's how you have. So you will typically have user in cell C0, and then C1 to C6 are, what you have, something like interferers, right? Interfering cell. So the key idea is that, so your signal power will be, and let's assume all of the, typically this will be the assumption that all base stations have transmit power P. Okay. So all of the base stations we assume in any cellular system. And so let's say there is this user, right? I'll just try to give you an idea. My drawing might not be perfect again. Let's say there is this user. So one user, let's focus on this user. So all of the base stations transmit at the same power. And if you assume a simple path class model, which is d to the power this thing. Right, you typically assume something like d to the power minus n, right? I'm just trying to be simple. Here, power received equal to something like power transmitted into d to the power minus n. right? And if the transmit power is the same, so I'll write it as PD to the power minus n. So if you have this thing as PD0 to the power minus n divided by summation over all I, P di to the power minus n, right? Where D0 uh, D0 is di, let's say. Di is distance from base station in cell Ci. Does this make sense? So just using notation that in the cell Ci, so if I denote this as cell C0 and something like C1, C2, C3, C4, C5, C6, right? For exact accurate diagrams, I would recommend you take the lecture slides in the video. I'm just trying to give an idea. So in the cell Ci, you will have some base station, and you want to figure out, and if you know the location of the user and the base stations, you can calculate the distance of the user from each of these base stations, and you put in the distance and you get this SIR. And if P is identical, if you assume this, all base stations have the same transmit power P. So then your signal to interference ratio becomes D0, or I can write it something like this, right? We can write it as summation I equal to 1 to 6 di by D0 to the power minus n whole to the power minus 1. This makes sense, right? Oh, actually, let me just write it cleanly. It will be D0 to the power minus n divided by summation I equal to 1 to 6 di to the power minus n. And because the powers are the same, so it cancels out, so it's no more a factor. Now, how do you want worst case SINR, right? Not SINR, SIR. Worst case SIR. This is the question. Now, how do you worsen this quantity? How does SIR become worse? So you have to make D0. How would you decrease this quantity SIR? Either D0 goes down or DI goes up for I equal to 1 to 6, right? For I equal to 1 to 6. So either your distance to your direct base, distance to your connected cellular base station goes down, or the distance to your interferers go up, right? Or both. So if you find a location here where the distance from base station is the largest, and also distance from interferers is the shortest, then that will be your worst case, right? That will be the worst situation. So typically the worst case situation is when you are on the cell edge. So for any user, the farthest distance it can go from the base station, if you can clearly see, is either here or here. From the geometry, you can see that, or any of the corners, basically, right? Any of the corners, any of the 6 corners here. So that will be worst case because you are farthest from the base station, you are most far away, and also you will be closer to the interferers also. You can see that you are already quite close to the two interfering towers here, and then the others are also okay, they are reasonable. So my understanding is all of these 6 corners of the hexagon are worst case SIR scenarios because of geometry, because of this geometry. And the rest of the calculation you need to check by yourself, or yeah, that is there. You can also refer from the slides or get a more, or just draw the diagram a little more accurately. But is the basic idea clear? Okay, thank you. Yeah, so that's the idea, that always in any cellular system, you will, in any paper or white paper, you will always read this notion of cell edge users. And so that is what I just showed, that if a user is at the edge of a cell, then that user's situation is worse. And so a lot of research goes into how can we design better systems and better protocols to serve the cell edge users. So there is a lot of literature. I don't want to get into all that, but this is an important problem. Okay. Any other doubts that you would want to answer? And yeah. Otherwise, I will just try solving some problems. But any other doubts? Okay, which book? I believe for this particular topic, I believe Professor has referred to Molish. He has actually prepared a website for the course. I'm not sure if it's shared. Let me, just give me a moment. I'll find it and I'll share it in the chat itself for your ease. And it has a lot of content, helpful content from like both, like it has book references and also it has supporting resources. I'm not sure. Okay, sorry, the website is not ready yet. I think it has not been published. But yeah, 1 second. So you can, one book that you can refer to is this book. You can find it online or in your libraries. By Rappaport, and Professor Rappaport is at NYU. And this is another book, also a classic textbook by Andrea Goldschmidt. And let's see if this book is. There's also a book by Mondish. Yeah, so Rappaport, Goldsmith, Mondish, many of these books are good. But I think the NPTEL, like specifically to solve these problems or to understand the concepts, I think Professor Koilpillai's lectures are good enough. If you go through them, if you go through the notes, and I think that should be enough. And to be honest, whichever topics you have any doubts about, these are really well-known topics. So you can simply search on them online and you will get help. You will get very concisely written articles from good websites that explain everything. So you might not even need to refer to a book. These are very well studied topics. And so what else? Co-channel interference and co-channel reuse ratio. What is its significance? Okay, I'll put this. One. Co-channel and what is its significance? So co-channel interference is essentially this is a phenomenon. This is due to this idea of frequency reuse. And why are we talking about frequency reuse? Because in cellular communications, so this concept of hexagonal cell geometry and all of these came about in the 90s, 80s and 90s, early 2000s, because then, and even now, bandwidth, like amount of electromagnetic spectrum that we have, especially for India, we don't have much spectrum available. And so we really need to find ways to efficiently utilize spectrum. And so that is why this concept of frequency reuse came into being. And so actually for frequency reuse, what you need is that you need to keep repeating the same frequencies at regular intervals, right? So actually I might have made a mistake in the previous diagram that I made. So let me just give another attempt at this. So sir, we are not getting sound. Am I audible to other students? I just want to check. Is any other student having audio issues? Otherwise, it's an issue at the person's end. Okay, some other students said that it's audible. So yeah, is this a reply? Okay, so by co-channel interference, what we mean is that, so for interference to happen, we need that the original base station and the interfering base station have to have the same frequency, right? Have to be using the same frequency band, or there has to be some overlap, because otherwise there won't be any interference. Okay? If you are using a different frequency band, then the receiver won't detect any interference. So typically the distance, like if this cell is using some frequency f1, then this will be using some frequency f2, and this will be using some frequency f3. Right? They will be using different frequencies so that the immediately neighboring cells do not interfere, because then the interference value will be very strong. But then this cell, which is over here, this will be typically reusing the frequency, right? F1, F1. So actually the diagram that I drew here is slightly inaccurate because these cells won't be interfering. So C0 will, the interfering cell C1 will actually be somewhere here, over here. These cells won't be interfering because these will be at a different frequency. But then you will have one interferer over here, one over here, another somewhere down here, another over here, right? So you can kind of see that it's one cell and then the next cell will be reusing the same frequency. And similarly, there will be another, it's a very, like you have to really picture it and do a lot of geometry here. And then, so again, if this is using F1, then this will be F1 again. This cell over here will be F1. I'll this thing. Then this cell over here will be using frequency F1. This cell over here will be using frequency F1 and similarly, right? So here you will skip one cell and then the next one will be using frequency F1. Typically that is how, so then you can see that you will have 6 interferers. One is this, one over here, one down below here, one above here, one on the left somewhere here, F1 again, and one over here. And so now you can just use just plain geometry and then you can do this kind of calculation and figure out your co-channel interference. So interference power is this is co-channel interference, right? Because in interference anyway is co-channel. You cannot typically have, like if people are using, if the transmitters are using different frequencies, you will not have interference. So like, yeah, so this thing I was drawing. So then for if my user is over here, and there is some downlink transmission going on. So let's say this base station is sending something, then these will be the co-channel interference channels, right? These channels, channel interference. Does this make sense? And like similarly on all the other sides also. So other base stations that are using the same frequencies will cause co-channel interference. And so when you calculate the SIR, you will have the signal power over here divided by the total co-channel interference, right? And if you are calculating SINR, which is signal to interference plus noise ratio, so you will have signal power divided by co-channel interference plus some receiver noise. So this is signal to interference plus noise ratio. These are the few things that we calculate. Now, co-channel, the other term that you mentioned, co-channel reuse ratio. Co-channel reuse ratio. What do you mean by co-channel reuse ratio? So, one second. So co-channel reuse ratio is typically, if I draw it over here. So you have this co-channel interferer, right? These two are co-channel interferers. So let's say the size of the hexagon, the side length of the hexagon is R, and you have to find out the distance between these two interferers, right? And this distance is D. So you have co-channel interference going on, and the distance is D. Now this I drew for hexagonal geometry, but you can draw it for any kind of geometry, any kind of deployment. So essentially co-channel, this one, reuse ratio is defined as D by R, right? Like this side length of the hexagon, 1 unit length of side. So R is side length and D is distance between interference, right? And so you can see that for this simple case, you can just show using thin geometry, because these are all 60-degree sides, that this distance will actually come out to be D equal to 3R, if I'm not wrong. It will come out to be 3R. This, if you try and use geometry. But yeah, in general, the formula is, I believe, D by R equal to √3N, where N is the number of the cluster size, I believe. No? Something like that. So these are actually little old topics. So many cases nowadays, this is not how networks are deployed, and various changes have come about. But so N, if N is the cluster size. Cluster size. What do you mean by cluster size? In this case, cluster size is 1, because we are defining this as one cluster, right? One cell is one cluster, and then we are just replicating it everywhere. But let's say your cluster size is 4. Let's say n equal to 4. Then so this is, you can calculate this ratio directly. Just you just have to plug in the formula. But just to kind of visualize, so if you have cluster size 4, then you have to first draw 4 hexagons like this. Sorry. This is 1, this is 2, this is 3, and this is 4, right? 4 hexagons. So this, you can draw a dark boundary over here. And so let's say this is your cluster, right? And over here, okay, so I have a question here, that is cluster size 1 valid and used in cellular geometry. I believe so. It is of course a very small cluster size, and so maybe not for deployments where you need to cover a very big area, but maybe in smaller networks. But yeah, as I said, in general, this kind of cellular geometry has undergone a lot of evolution, and now various different things are done. Like in 5G networks are not at all deployed like this. There are like macro cells, small cells, picocells, femtocells. So there are like various different kind of architecture is used. So when I did a similar version of the course at IIT Kanpur, we were just briefly taught this. We weren't really taught this topic in that much detail. So, so I'm not an expert on this, because I haven't been in industry at that time when this was popular. This is a little outdated, but it's still good to visualize and have an idea of how things are planned out. So anyway, cluster size. So let's say this is cluster size 4, which means uh, these four base stations, they form a cluster, and so the actually co-channel interference will then become formed here. something like, yeah. So this is a second cluster, as you can see. So this is one cluster of four, this is another cluster of four, and you can draw similar 6 more clusters around. And so you have your familiar setup where this is C0 and this is C1 and so on. Yeah, cluster size 1 means that every adjacent cell will be a cotenance. You're right. And if its cluster size is more than 1, then you have to draw and see. So then you have one following, like the next cell will be a cotenant cell and things like that. So yeah, that these kind of things are there. Yeah. So yeah, here you can see that this ratio will increase because so why this n factor comes into the picture, because then if you are using that kind of same logic, you're finding the co-channel interferer, then it will be somewhere over here. Somewhere over here, and you will have to jump through more of these hexagons, and so this ratio increases. So anyway, this is the formula that you can simply use. Don't have to really visualize it for exam purposes, but yeah. Is Did it help any other doubts? Yes, Abhishek, I believe. So the significance of this is co-channel reuse ratio is that like I believe how much how it's kind of an idea of how many users you can support with interfering frequencies. My guess is that the higher the co-channel reuse ratio, um, the more users you can support without having to without having to face this interference from nearby channels. So, but then there are also other problems that if you cannot just keep increasing the cluster size, because increasing the cluster size causes other issues. So you have a drop in throughput if you increase cluster size. It's there in the formula. So you have to find a trade-off. Okay. Okay. It's 3:55. And, any other doubts? Numeric questions similar to assignment questions. Okay, I'll try. I believe I already have kind of given you some idea of how to solve question 15, which is or essentially 14 to 14, 15 told more or less. 14, 15 and 16, 17 also you can work out now, because tier 1 interferers are essentially these are your tier 1 interferers that are just one removed. So tier 1 interferers, and these are the most important interferers because they are the closest interferers, right? And so the rest is just using that geometry to calculate, and for hexagonal geometry, you have some patterns of root 3R will come up. And so rest you need to really do the calculation yourself. And I also told you this formula of SIR. SIR is essentially signal power divided by interference power. And SINR is, so there is one question that involves SIR and SINR. So here you have the same signal power and photon and interference, you just have to compute the noise. And for noise also you have standard formula, so you can calculate. And I will be solving some problems with regard to this. Actually, just now there are some simpler problems in the assignment, so I will try to give you an idea of how to calculate noise and how to calculate part loss and things like that. So those are the basics which you will eventually need to solve these kind of complex problems. So, okay. Let's see if there are any other doubts. Okay, if not, let me go and answer these questions. Okay.
Sir, will you please once again explain that tier 1 interference, which is asked in assignment? I think.
Yeah. Tier 1 interference is essentially interference from the closest interferers, which is these C1, and then you will have C2 over here. Like theoretically, you will have an infinite number of interferers, right? Even after this C1, you will have some other cell here, like let's say C7. This will also be an interferer, and so on and so forth. So you cannot just keep doing an infinite sum, right? You typically have to just solve portions of the problem. So by tier 1 interferers, you mean the interferers that are actually the closest interferers to you. So the closest interferers will be these C1, C2, and then another interferer over here, C3, and this interferer over here, which is C4, and then you will have C5 and C6. So essentially the 6 closest interferers. So C1 to C6. So these are your tier 1 interferers. And typically, we are mostly concerned about tier 1 interferers. Tier 2 interferers come later. So they are even farther away, and their impact on the received signal is less. Is it clear?
So we will have to calculate C2 in case of C1. If tier 1 interference is asked, then we have to calculate interference from C2.
Okay. By here I meant C0 to be the reference point, right? This is my reference point. This is where my user is. And so from this reference point, you can see that the closest interferers are 6 of these, right? You have this C1, C2, C3, C4, and then you will have C5, right? C5 somewhere here, C5, and then similarly you will have C6 over here. So these are all. So all of these 6, C1 to C6, are your tier 1 interferers.
Okay.
Now, if you want to find out tier 1 interferers to this user over here, then you call this C0. You refer to this one as C0 and then find out C1 to C6 around this. So your reference point you can always mark as C0, and you find out the 6. Like typically hexagonal geometry will have 6 co-channel interferers, 6 tier 1 interferers. Then tier 2 will be 6 more. Like just proceeding by geometry, it will be 6 more, and then so on and so forth. So whichever is, wherever your user is located, you pick that cell to be C0, and then you see around it. Is this clear?
Yeah, yeah, sir, somewhat.
Uh, okay, so this is actually this topic will keep on coming in later 1 or 2 weeks too. So you will have time also to a little bit. If this week it's not very clear, not very convincing, next week you will have more exercises, more problems, and it will become more clear. But there are some more basic topics that need to be clarified in this week's session itself. So I'll do that. So so the path, so this is primarily there is this path loss model, right? Path loss models, and these are things that you have to deal with in whenever you're designing wireless system. If you want to figure out that how much power is lost, my signal travels a certain distance d. Um, so,
Sir, it is,
so d is typical. Yeah.
sir,
Sorry.
it is asked in assignment find out worst case SIR for the user due to only tier 1 interferer. So worst case
Yeah.
SIR, we know SIR means desired signal power upon interfering signal power. So we have to calculate worst case SIR means what we are not getting.
Worst case SIR I had explained just some time back. Some other student had
Okay.
asked. So I'll just repeat it here very briefly. So um, for worst case SIR, what you need is that you need your distance to your own base station, to your own cell's base station. You need that distance to be right. Hi, am I audible? Can somebody confirm? I'm sorry, the network issues. And unfortunately, the Zoom chat also what it is. If somebody asks doubts in the Zoom chat, please repeat your doubts if you can. Can everyone hear me?
Yes, sir.
Somebody just okay. So some discussion was on regarding tier 1 interferers. So tier 1 interferers are the closest interferers, as I was kind of drawing. And yeah, there was a
Voice is
question
clear.
regarding
Voice is clear.
voices.
Okay.
Okay, thank you.
Clear. Achha, sir,
Thank
one question is that from the next time, can you make this your live session in the Zoom meet? Because I feel that this is Zoom Ask is not well actually. That's the
Which
problem
part?
actually. From the next time, can you arrange this live session on Zoom Meet platform?
Google Meet? You mean Google Meet? No, I don't
Google
think I'm allowed.
Zoom Meet.
This is Zoom meeting. I don't know what.
This is Zoom Meet, the Google Meet. Otherwise, actually, last time your Monday and Tuesday session was on Google Meet, and that was very success actually.
That is fine. I don't think Zoom is an issue. There was some network fluctuation.
Actually, I feel some problem to join your live session, but I have to wait for 30 minutes, 40 minutes, then I can join. There are several issues. That's why that's the problem.
I don't think so. I have used Zoom. Used Zoom without any problem on my previous session also. I think I had disabled all of those things that sometimes they ask. I had disabled waiting room specifically for this purpose, so that students can just join in, and every other student had joined in. So I don't know, and at this stage, I'm not allowed to change the meeting link, because then it will cause a lot of disruption and
no, I want to tell that not at this moment, that from the next time, from the next Sunday, if it is possible. That's my request. Okay.
Yeah.
Okay.
So anyway, we are discussing about path loss models, and so what we want to figure out is that how the distance, how does the distance from base station affect the signal strength, right? So that is something that was an important problem, and the one commonly used path loss model is the free space path loss model. It is a very simple path loss model. So we have free space path loss, right? So the free space path model, in this model, the power, so this is very simple, that the transmit power is equal to the received power times 4 pi d by lambda squared, where d is the tx, let's say, transmitter and receiver distance, right? So this is the free space path loss model. Very simple model that does not capture a lot of things that happen due to environmental effects and so this is essentially the loss in signal strength which will happen if you transmit in signals in vacuum on like just air, this very unpolluted simple air without any interference or scatterers. So so here lambda is the wavelength, as we know. And one important formula is, we all studied in physics, but we should always keep in handy, is this notion that C equal to F lambda, right? Or carrier frequency times lambda, where Fc is the carrier frequency, right? And C as we know is speed of light. Speed of light, which is 3 into 10 to the power 8 meter per second. Okay. So, so this conversion has to be seamless in general. And no, the reason I was emphasized on it is in many problems you will be given this value of Fc, and you have to convert bit to lambda. You have to convert in order to get lambda, which you will plug it in over here, right? Or you can maybe rewrite this formula as PR received power times 4 pi d, and then lambda is C by Fc. So you just write it as this. Just if you just do substitution, you will get. So either way, this interconversion needs to be handled. And so typically the problems in this kind of system, and another notion is which was also discussed in the last last session, is dB watt and dBm, and how do you calculate or interconvert these two. So dB watt is essentially nothing but 10 log of power over 1 watt. So when you are using the base unit as 1 watt, then the dB value that you get is dB watt. And if you use the base unit as 1 milliwatt, so you are given some power. And if you use the base unit as 1 milliwatt, then the value that you get is dBm. And as I shown in the last lecture, so essentially the interconversion comes out to be dB watt is the dBm value is typically dB 30 plus dB watt value. So whatever value you get in dB watt, you add 30 to it, you get dBm. The same equivalent dBm value. So this dBm to dB watt conversions sometimes you will need. So anyway, first very simple problem is that you are given transmit power, let's say for free space buffer, you are given transmit power as something like this one watt, let's say, and received power is something like 0.1 watt. So what you can do is immediately convert to dB scale. So this will be 10 log 1, which is 0 dB watt. And this will be 10 times log of 0.1, which I believe is minus 10 dB watt. Just log and decimal conversion. And so this formula that I wrote in linear scale, this can be converted into dB scale. So what we'll have is, we'll just take logarithm on both sides, 10 log on both sides. And so this will essentially become PT in, and we know that product means we are adding up to logarithm scale, right? So we'll have PR in dB watt equal to PT in dB watt. So this is the original transmitted power. And then we'll have a negative term because of path loss, right? And we'll have 20. Why 20? Because 10 because of the linear to dB scale formula, and then you have 2 from the exponent term. So this will be 20 log 4 pi distance divided by lambda, right? This is the formula. And okay, I missed one data point, that carrier frequency is told to be, let's say, 900 megahertz, right? And so you know PT, you know PR, you know the carrier frequency, which means you also know lambda. So what is the value of lambda here? We can calculate it first. Lambda will be C equal to F lambda, so lambda equal to C by F. So C is 3 into 10 to the power 8 divided by F, which is 900 megahertz into 10 to the power 6. If you cancel, that comes out to be 1 by 3 meter, right? So this is the wavelength. And what you have to find out here is D. So you can simply solve and get the value of D. So basically, the question will be that if this is the received power, what is the distance of the user from the base station? Something like that. So D is distance of user from base station, and you have to find out this one. So you can just plug in. So this will be how much? Minus 10 equal to 0 minus 20 log 10 4 pi d divided by 1 by 3. So I've just cooked up numbers, so I don't know the exact answer. And if somebody can volunteer and solve this using calculator. But so this will come out to be 12 pi d equal to 10 to the power. So if you take 20 this side and 10 this side, so 20 log 10 this same equal to 10, so it will be 0.5 and 10 to the power 0.5. So somebody can just put in into the calculator and give me the value of D. So these are very simple problems. And you will get some value. So we will have similar problems in assignments and exams, and this is roughly the idea of how to solve. You just have to substitute, and then some complications arise where you are given some extra information, and the basic idea is the same, but you are given some extra information, and those models are also tweaked, and then you have to figure out how to solve. So now let's say you are told that this thing. This is, I believe, something similar, and label it as question 1 maybe. First. Now let's say you are told that your original signal power, let's say P is equal to 1 watt. So this is the power of signal. Let's say denote it as PS. This is signal power. So you have generated a signal with a power of 1 watt, and you are told that you have some antenna gain. So you have some transmitter antenna, and the antenna is using some kind of special circuitry, and it has an antenna gain of 10 dBi. Right? dBi. So how do you interpret dBi? So it doesn't really matter, because as you can see that whether you are using dBm or dB watt, it's just you are just adding 30. That's all. So if the dB watt value goes up by 10, the dBm value also goes up by 10. It's a linear relation, right? So you can essentially just add the antenna gain to the signal power, and then you're also told some kind of amplifier gain. You have some amplifying circuit there, amplifier circuit, and this is also, let's say, 5 dB. This is like 5 dB. And then so you have this, basically you have some signal, and you have some kind of antennas that connect you to an amplifier. And so I'm just writing this combined thing as an amplifier. I think I drew it now. You have an amplifier circuit, and you have all of your gains, and then you have a cable, and then you have some kind of transmitting antenna. Right? And here you are radiating the signal to the air. And now you are told that there is this cable has some loss. So you are told cable loss is 5 dB. So you have to find out something known as EIRP, which is effective isotropic radiated power. Now, how do you find this thing out? By isotropic, what do you mean by isotropic? Isotropic means that your signal is just radiated everywhere in all directions uniformly. So you're just throwing it all into space. You are not doing some kind of beamforming to concentrate the signal in a particular direction or anything. You are just radiating it in the air. And so what will be your EIRP in this problem? So EIRP will be obviously your original signal power to begin with. So this is 1 watt. This is where you have to be careful. This is linear scale and all of the gains are provided in dB. So in linear scale, if you are using these values, you have to convert them into linear scale as well. And then you will have to multiply, right? So this will be power times all of the gains, right? Let's say if I denote it by G. So this is in linear scale. But in dB scale, I'll be taking logarithm, right? So I'll have to add. So because multiplication in linear scale becomes sum in dB scale. So I'll have to add all of the gains over here. Add or subtract. If there is a loss, I'll subtract. So 1 watt is, so this I can write it as 0 dB watt again. So this is 0 plus, let's see what are the gains. So I have 10 dB antenna gain, I have 5 dB amplifier gain, and I have a 5 dB cable loss. So 10 plus 5 and then a minus 5. So then what I have is I'm radiating 10 dB watt. That is the answer for this problem. But for different problems, you'll have different values, but the concept remains the same. That you have to add all the gains, subtract from the losses, and then you have to see how much gain you get compared to the initial power. So this kind of problems you will get. Lot of them. And what else? This is the side. Then any questions in this kind of problem? This will be pretty common. And then for Parthenos, then you have some slightly advanced model, which is this breakpoint model, right? This write it down. Breakpoint model. So what the breakpoint model says is that path loss is equal to 4 pi d some kind of breakpoint distance by lambda squared, and then you have d by d break whole to the power n. So where d break is known as the breakpoint distance. Now this formula obviously holds for d greater than d break, and for t less than or equal to d break, we'll have the usual 4 pi d by lambda whole square. So what does this formula or this expression mean? Is that let's say I have a transmitter here. I have some kind of let's say draw it in this way, some kind of radiating antenna over here, some radiating signals. So up to a distance of d break, so the user is, let's say the user is here. No, let me draw it correctly. So let's say the user is here. User is here and the distance of user is d. So I'm varying d. So I have some distance d break. I'll just label this as 0 and this as d break. So up to distance d break, this formula is 4 pi d by lambda whole square. And then after that, I'll have d by d break to the power n. Something like this. Right? So up to d break, what I have is I have simple free space path loss as discussed earlier. So it's just 4 pi d by lambda whole square. And after this distance, it's not just path loss, then we are considering other effects also. And so we'll consider the impact of path loss up to the d break distance. And after that, I'll have some other exponent n. N will be typically be greater than 2. N will typically be greater than 2. So after that d break distance, I'll consider the path loss to be a lot more severe. Right? So that is one version of path loss model that is used. You can solve a simple problem. Let's say d break is given to be 100 meter for some system, and my value of n is, let's say, 4. Okay, and the maximum so I have the base station, and let's say I have some specification that maximum path loss that I can tolerate at my receiver is something like 100 dB. So I cannot tolerate more than 100 dB path. And so I have to find out the range. So what is the, by range is what, when we typically say range in context of wireless communications, we mean that what is the maximum distance to which I can serve a user. So what is beyond which, what is the maximum distance, and after that distance, I will not be able to serve the user properly. So how do I compute this range here? So let's typically range will be, let's assume for now. So here there is one problem, that is we don't know the value of R. We don't know the value of R, and we don't know which of these formula will apply, right? Because if R is less than D break, then we have to use this formula. If R is greater than D break, then we have to use the above formula, right? So typically we can consider that, we can assume that R is greater than D break for now. We'll have some larger distance that the coverage range should be greater than whatever breakpoint I'm considering. So with this assumption, we need to solve and see if the assumption is valid. If the assumption is not valid, then we need to go back and change the assumption. That is the idea, right? So if we assume R greater than D break, then I'll have this formula, the formula above. And so path loss, this is a linear scale. This formula is a linear scale, so I have to convert it to dB scale. So 100 value in dB, so I have to take 10 log on both sides, will be 20 log 10 4 pi d break, which is 100, divided by lambda. So I was missing one value. Let's say the carrier frequency here is 1800 megahertz, right? So the value of lambda, quick calculation, C equal to F lambda. So lambda is equal to C by F, right? So this is C by F. So this will come out to be 1 by 6, if I'm not wrong. So this thing plus some 10 n times this, if I'm just doing log, so 10 times n value is known to be 4. So I have taken n equal to 4, so I substituted directly. 10 times 4 times log. I want to find out the range, right? The maximum distance. So that is d here, right? I want to find out the maximum distance, so d, and the breakpoint distance is known to be 100 meters. All right, so this is log to the base 10. And get the value of d in meters, get the value of range r in meters. So can somebody calculate and tell me what is the value of r? I haven't solved this one. I'm just making the numbers up. So, and this might actually lead to an abstract solution. I really don't know. Let's see if I have my calculator nearby. Otherwise, if somebody can quickly solve and tell me the answer, it will be good. What's my calculator? Let's see. 4 pi into 100 into 4. Okay, so I have solved. I just did it in my calculator. If somebody can verify this, it would be great, because as I said, I just made the problem. Like, I use my own numbers. Don't know. So this is the value of r that I know, which is 364.18 meter. And what we need to check is whether our initial assumption is correct. So d break is, we had already written, d break is 100 meters. And r is 364. Right? 1 second. Okay, there was some lag, but I think the screen is visible now. So our assumption is correct, and so then this is our answer. But let's say if we were making some mistake, if there was some other values, then I might have had an r value here that is smaller than this breakpoint distance, and then my assumption is wrong in that case, which means I'm making some mistake, and so I have to go back and use this formula. Is this clear? This kind of is one kind of slightly tricky situation that can come, and that's all. I think this is one major point. For the noise figure, I think there is one question on noise figure. I think the formula is very straightforward. It's given in the lectures. and simply just use. It's a very formula-based question. There is this question is a bit conceptual. We can go over this a little bit. I label this one as question 3. And this is actually somewhat related to the previous week's content, but okay. So,
Sir, so excuse me,
yeah.
sir. Yeah,
Yeah.
you are taking one by one every question from assignment, na?
No, I'm not taking the exact assignment questions. I'm doing similar questions to the assignment. I'm not solving the exact
No,
assignment.
not solving, but similar type of questions, na?
Yeah, I'm trying to. Yeah, similar.
So have you covered, sir, that worst case SIR, those questions earlier, because I joined late?
Yeah, I did. I did cover. I did cover and I did discuss. That was one of the very first doubts that I had. And so I think this recording will be there, so you can check later. But
Sir,
I did
where
cover.
this
I gave an idea, but I didn't exactly solve the entire thing. It's a long question.
Yes, you are not solved, na? So will you take similar question related to this
No,
also?
that no, I think I've given enough idea, and with that, it should be possible to solve. It's not that difficult. Like as I said, like I was also doing this one. So you have 4, like this kind of cluster of 4, and you can, and so you have to do the geometry yourself and find out these distances from the tier 1 interferers. And once you find the distances, you just have to plug in this formula and you get your answer.
Yeah, sir, but it is looking difficult little bit. Means if you take actual problem, maybe in next session, no issue. But then
you will
that will
get eventually you will get solutions to all of these assignments before exams. I think they'll periodically keep releasing solutions, but I believe this is a graded assignment, and I'm not allowed to just give
no
solutions.
similar kind of questions, sir. You are taking like here you are taking, na? So
Yeah, I'm
similar
trying
kind
because
of,
in these questions it is somewhat easier. These are just
yeah,
very just numerical questions, and
yes.
I can just change values and do similar questions. But in that particular cellular geometry question, it is very difficult because there is very little that I can change in those questions. Like uh, I I cannot actually solve a similar question because it will be like solving the same question. There is very little variation that I can do in those questions. It's all the same
Uh,
geometries, same thing. So
yeah, but that's means that's why it may go difficult for us.
yeah, you try your best and submit your solution, and then eventually it will be graded, and you can see the actual solution, and then you will learn. And yeah,
Yeah, sir.
uh,
That is.
okay. And yeah, okay. So anyway, let me just quickly.
Yeah, sir, where we will be getting this? Because last session we didn't get on our portal, means on this subjects portal.
Which session?
Last discussion session means in last week's discussion sessions, Sunday, Monday, Tuesday
Yeah.
sessions, we didn't get them uh, where we have got
The video.
assignments and video lectures. There, that session is not available.
You can check with the NPTEL team on that because we are doing what we have been asked to do. We once this session gets over, I'll upload the recording on YouTube, and my YouTube channel link I have shared in the chat also, but I have actually also shared with the NPTEL team. They have asked us to maintain a sheet, And so over there, we are sharing the YouTube link videos and the links to the drive. And whatever has been asked of us, we have done. And so it is their responsibility really to coordinate and like in the same way that you
Sure.
got access to this session's link, you might have gotten some kind of email, right? Notification
Yeah.
that this is the
Yeah. Yeah. Yeah.
link.
Yes.
So
In similar way,
they
we want these sessions also to get
yeah,
shared
you
with
can.
us.
I would request you to ask the NPTEL team because we are doing what we have been asked to do from our end. Now, if they are not being able to send it to you, then that is some kind of problem they are having. I'm not sure
Okay.
what. So
Okay.
we are. I'm doing what I've been asked to do. I'm taking the session. I'm making the uh, uploading it on YouTube and giving the
Yeah. Yeah.
link
Yeah.
to
That
them.
is correct.
So
Yes.
some delay must be happening at there.
Yeah. Okay. We will ask them this
Yeah.
question.
Yeah. Okay. Let's see. So this one kind of path course model, this is thought that this tricky case can arise. So you discussed. What else remains to be discussed? Okay, this sometimes you are given these BER targets, right? One assignment question is on the BER target. Let's say BER target is 10 to the power 6. BER stands for bit error rate. So this is actually not this is actually some topic that is taught in any standard digital communication course. Now, how do we calculate the bit error rate of a certain symbol or certain constellation? Uh, but and still just write the formula. It's so the typical formula for BER is the Q function. Uh, Q function of root over number of bits per symbol. So n times the energy per bit divided by n naught. I'll just write down the terms. N is number of bits per symbol. EB is energy per bit, and n naught is noise power, right? That is the typical notation that is used. So this is a formula for bit array. So, so essentially the symbol energy is equal to n times the bit energy. That is how this comes. So, so you can this is based on the notion of the Q function itself. So Q function, as we know, is that like for a standard normal Gaussian distribution, normal 0, 1, the Q function is probability. Q of x is probability that this random variable x is greater than x, right? We believe this. We just you can, so this is like if you have a value small x, um, you want to find out this area, right? So this is the Gaussian PDF, well-known bell curve, and you want to find out the area, this area, the shaded area over here. So this is known as the Q function, and this does. So this is not analytically something that compute, but you Q function table calculators online that do the job for you. So and you have to use either you have to use those tables or you are provided the values that you need in like in the question itself. So let's see. So I'm given, so let's say I'm told that I'm using QPSK modulation, right? Or let's say something like 16 QAM modulation. So in 16 QAM, I have 4 bits per symbol, so n is equal to 4. This much I know. And then the first question is that what is the value of EB that I need to achieve this value of BER? So this is something that we should know how to solve. So BER I know is 10 to the power 6. So that is Q function of square root of 4 times EB by N naught. Right? And here, so I need to find out the value of, let's say instead of EB, I want to find out EB by N. So what is the bit SNR that I need? So I can solve this. How can I solve this? I need to use, so EB by N naught will be 1 by 4 times Q inverse of 10 to the power minus 6 squared. Right? So it's just, you can, this is a simple method, okay? So Q function, like we can calculate Q function, we can also calculate Q inverse function. There is a MATLAB inbuilt function, and also there are other tools. So I am using one of the online tools available right now, just to do a quick calculation. Ten to the power minus 6 should be 0 for 4 by. Yeah, I think I'm right. Let's find so I'm getting this value to be, let's see, 1 by 4 times 4.75 squared, right? So it comes out to be 5.64, something like that. So this kind of calculation we should know how to do. My bad. And so now on top of this, there are usually that is something that you already studied in the previous week session. That is, if you are given the, let's say, the Boltzmann constant, so you know how to calculate N naught. N naught is nothing but 10 log of, like in dB, it will be Boltzmann constant Kb times temperature times the noise figure. So yeah, that is typically the value of. And so typically you will, in your question, you will be provided the values of Boltzmann. Boltzmann constant is anyway known. I think 1.38 into 10 to the power minus 23, if I'm not wrong. Or anyway, you can find it online. You'll be given the value of temperature, and you'll be given the noise figure. And so you can just plug it in and calculate. And so you'll get a value of N naught, depending on the question. And so you will know the, and if you know N naught, you will know the EB here. Okay. And if you know EB, you can
Sir,
also
what
find
is
out.
F? Sir, what is F in this?
F stands for noise figure.
Okay.
F stands for noise figure. It is this noise figure is essentially input, SNR input divided by SNR output. And
yes.
so this is discussed in the lecture. It's a simple concept. So this is usually provided in the question. The noise figure is so and so dB.
And sir, what is Boltzmann beta B? That is Boltzmann constant. No, you are saying?
Yeah, this is Boltzmann constant.
So its value is how much?
I don't remember exactly. It's one of those
Okay,
standard
okay.
points. It's probably my memory says it's
Yeah,
1.38 into 10 to the power minus 23. But it's a well-known quantity.
yeah. Okay, sir.
Yeah. So you can essentially from this, I just wanted to discuss this handling of the Q function business, and from here you can essentially calculate SNR, which is uh, essentially the formula of bit error rate is Q function of square root of SNR. And that is where this formula comes from. So Q function of square root of SNR. And so SNR is nothing but your symbol power, which is N times ED by N naught. So this is your SNR that you need. And so sometimes, so the other things you can just figure out. So let's say you are told receiver sensitivity, receiver sensitivity. So some, let's say PS. So what will be the receiver sensitivity that you will need? Here you just need to calculate this noise power N naught in dB. So you know the noise power, and then you will add to this target SNR, right? Because you need your receiver to receive signal of at least this much power for the receiver to be able to detect it. So you need it to be at least this. So you have calculated the minimum SNR that you need for it to be able to achieve a bit error rate of 10 to the power minus 6. And so you just add that to the noise floor. This is, as we know, this is called noise floor. You just add it to the noise floor and you get the receiver sensitivity, that what is the minimum power at which I should receive the signal at the receiver for it to be detected. And then there are some things we had already discussed. You can have small modifications to it where you'll be given a certain antenna gain and cable loss and amplifier gain, and you will just adjust it over here. So in the transmit power, you will be adding the antenna gain and receive antenna gains and path loss margins and things like that. So that you can figure out. Any other questions? Yes. Okay, I'll end the session then. And as I said, everything I'll make it available on at least at my end, I'll make it available. I hope they send it out to you as soon as possible. And you can check up with the NPTEL team and ask them to, uh, you know, it's not an issue at our end. We are providing everything.
Sir, can we get your contact number if we have some doubt? Can we discuss it?
No, I don't think we are required to, or I don't think I'm comfortable sharing my contact number. It's a large course, and I don't have the bandwidth to address doubts. So this is 2 hours a week is my commitment, and this is the time I'll help you to the best of my ability. Otherwise, I also have my other commitments, so I won't be able to commit to more than this. So,
Okay. Yeah.
okay. Thank you. I'll end this session.
Yeah. Sir, please, can you send a link of this on YouTube?
I will upload this video on YouTube. I had shared the YouTube channel link. I can share that again. But
Yeah.
as I said, we are already anyway providing this YouTube links and everything uh, to the NPTEL team, and they are supposed to be sharing it with you. And so I don't know if if it's a problem at it's a problem at their end maybe, because we are we are doing our part. Okay. Anyway, share the playlist in the Zoom chat. Okay, thank you. It's almost 5 o'clock. Ending this session.